Hello everyone, I am Phani Paladugu, Product Management Professional from Synopsys. Welcome to the presentation on reimagining SerDes for scalable AI, architectures, bottlenecks, and breakthroughs. In today's presentation, I'll be using a SerDes more often. It is a short form for serializer, deserializer. It's a high-speed interface that is used for data transfers. Today's agenda covers AI workload impact on interconnect designs, signal integrity challenges at data rates, architectural trade-offs, and future directions for certain. The generative AI leads to exponential growth in compute demands. The model sizes are doubling every 3 to 4 months. Despite the parallels, the training times are increased to weeks and months. Due to increased compute demands, the memory and interconnect bandwidths are falling behind to support the compute demands. With this, it puts a lot of pressure on the interconnect and memory technologies to deliver higher bandwidths with a lower power and lower latency. The conflicting demands for SerDes in AI era. So as I mentioned earlier, in order to support the increased compute demands, the interconnect bandwidths needs to be increased. That means the data rates for the SerDes are going high and high. If you see the current transition, the Ethernet SerDes are moving from 112 gig data rates to 224 gig data rate, and the PCIe is moving from 64 gig data rate to 128 gig data rate. Even with increased data rates, the power efficiency is also very key. So in order to meet the system requirements, we have to ensure the power efficiency targets are well within the limit. The current SerDes, the power efficiency is around like 4 to 5 picojoule per bit. That needs to support the long reach channels of order of 45 to 50 dB. In addition to this, we need to deal with the signal integrity challenges as well at a higher data rates. With increased data rate, the signal integrity challenges are becoming more and more. At a higher data rates, the channel loss is very high, and it leads to more reflections as well due to the discontinuities in the channel, and the crosstalk impact is also very high. So in addition to that, we need to understand the workloads where this particular service is being utilized. So understanding the workloads will help us to better get the use case, and so we can optimize the service to meet all the requirements. The conflicting demands are creating a design paradox that demands innovative approaches to meet all the service requirements. Let's try to understand the AI workload impact on interconnect designs. So as we know, like there are two different workloads, like a training workload and inference workloads. Let's start with the inference workloads. Inference workloads are more of a bursty topic with the variable loads that needs asymmetric bandwidth requirements. And inference workloads are more of a memory bound than a compute bound, and the latency is very key here. If you look at the training workloads are more of a compute bound, and it needs like a very high bandwidth to move the higher data. And the latency is also very key here. So for the distinct workload characteristics requires a specialized SerDes design techniques. For AI, before we start designing the SerDes, we need to better understand the exact use case and the workload requirements. That will help us to optimize the performance, power, area, and the latency. Let's touch base on the signal integrity at multi-gigabit data rate. The channel characteristics varies with the frequency. The channel loss is very high at higher data rates. If you look at the Ethernet SerDes at 224 gigabits per second data rate, it has to support channel loss of order of 45 to 50 dB to meet the system level constraints. Similarly, the PCIe Gen 7 SerDes at 128 gigabits per second needs to meet a channel loss of 35 to 40 dB. With increased data rates, we have a design constraints on the jitter as well as like increased intersymbol interference increased reflections due to discontinuities in the channels, and increased crosstalk effects. So as we move forward to 24 and beyond, we need to implement novel equalization techniques to address all the signal integrity challenges. Let's touch on innovations in SerDes design. The traditional NRZ-based SerDes implements a feed-forward equalizer on the transmit side and continuous time linear equalizer followed by a digital feedback equalizer on the receive side in order to support long reach channel requirements. As the data rates are increasing, the signaling scheme for SerDes has moved to like a PAM4 from NRZ. All the PAM4 SerDes are DSP based. These SerDes leverages a multi-tap feed-forward equalizer and multi-tap digital feedback equalizer and optimized continuous time linear equalizers along with the high performance data converters to meet the stringent signal integrity constraints. If you look at adaptive equalization, real-time adaptation techniques are implemented to fine-tune the SerDes parameters to meet the channel characteristics. Machine learning for SerDes. So there are machine learning algorithms are implemented for calibration and adaptation. Advanced CDR and forward error correction techniques. The clock and data recovery is a key function that is being implemented on receiver side to recover the clock from the received data. So advanced clock and data recovery circuit uses a digital bang phase detector and a multi-phase sampling to improve the accuracy of the sampling, and spectrum clocking is implemented to minimize the electromigration and IR drop. In addition to that, hybrid architectures are selected to balance the performance versus power. Forward error correction circuitry. Forward error correction circuitry helps to optimize the bit error rate by minimizing the bit errors within the SerDes. There are various standard FEC circuits are available out in the market like Reed-Solomon FEC and LDPC FEC. A specific FEC can be selected based on the channel performance and power and latency constraints. Let's look into the architectural trade-offs for the SerDes design. Yes, as I mentioned earlier, performance, power, area, and latency are the key parameters. This leads to a multi-dimensional system design challenges. So we need to address and optimize all these four parameters to make sure it meets the system requirements. So the next one is looking at the different architectural options. Analog architectures versus digital architectures. The legacy SerDes are more of analog architectures with higher data rates, and the signaling scheme moved to PAM4. The latest PAM4 are more of a DSP based and moving towards the digital architectures to enable all the process scalability advantages as well as to implement the voltage scaling to further minimize the power. For SerDes, the configurability and scalability are a very key parameter. As I mentioned earlier, in order to support wide variety of bandwidth requirement, SerDes can be configured from 1 lane to 16 lane for Ethernet, and similarly like the PCIe use case. So configurability is one key important parameter for the SerDes, as well as reconfigurability is also equally important. So if we look at multi-protocol SerDes, the same SerDes can be configured for Ethernet as well as the PCIe based on the use case. The power challenge. AI workload demands a few hundreds of SerDes to be used in order to meet the compute demands. So the power efficiency is very key for the SerDes. There are various techniques can be implemented starting from circuit to the system level to optimize the power. If you look at the circuit techniques available to optimize the power, that includes supply voltage scaling, adaptive biasing, and clock gating. If you look at the architectural optimizations, we can implement the power islanding and the workload aware power states that can optimize the architectural level. If you look at the system approaches, there are few ways of optimizing the power by implementing the dynamic voltage and frequency scaling, as well as thermal aware floor plan and placement techniques also will help us to optimize the power. The holistic solution strategies for the SerDes design. So before we start designing the SerDes, we need to analyze few things and understand the use case. Then we can optimize the SerDes solution for a specific application use case. So in this case, we need to start with the workload analysis. We have to understand the exact workload patterns and the traffic use case. So that will help us to better understand the service use case, and it will help us to optimize the performance. The signal integrity and power integrity challenges. We need to build a end-to-end model that includes the transmitter, receiver, and the channel, including the package and PCB traces, and analyze the system level performance and fine tune the characteristics of the individual modules within the transmitter and receiver based on the channel characteristics. That will help us to optimize the performance, power, area, and the latency of the individual modules. The architecture selection. So architecture selection means we need to better understand the application use case. For example, the ultra accelerator link can be used for scale up architecture within the data centers. Similarly, ultra ethernet can be used for scale out architectures for data center architectures. So these particular configurations are optimized for latency and power and performance. In addition to all these three, we need to look at the physical design as well. We need to optimize the SerDes for north-south as well as the east-west placement in the chip. So most of these AI applications needs hundreds of SerDes lanes. So we will be able to place all these SerDes in on north side, south side, east and west side, and find optimal package escape routes to not to impact the performance. Let's touch on the future directions in SerDes for AI. So, as we discussed earlier, we are at a data rate of 224 gig for Ethernet SerDes, and we'll be moving to 448 gigabits per second data rate in next to 2 to 3 years. Similarly, we'll be transitioning to PCIe Gen 8 at 258 gigabits per second from PCIe Gen 7, which is at 128 gigabits per second. UA link also will be transitioned to 224 gig to 448 in a couple of years. In addition to these technologies and the standards, the co-packaged optics is becoming more and more popular. This will help move the optics closer to the switches and the AI accelerators. That minimizes the channel loss requirement and eliminates the need for the which in turn optimizes the power and performance. In addition to the co-packaged optics, SerDes for advanced packaging also becoming more and more popular with the multi-die solutions, chiplets, and 3D packaging applications needs fine-tuning the lot of SerDes requirements to meet all these latest technologies. So these technologies promises 5 to 8x improvement in the bandwidth with a reduction in power by 2 to 3x. So this will help us to further improve the performance and minimize the power. The key takeaways from the presentation are AI workloads are fundamentally reshaping the SerDes requirements. Power efficiency and latency are key design constraints for the SerDes. Signal integrity requires increasingly sophisticated approaches. Heterogeneous SerDes architectures are the future. This concludes my presentation for today. Thanks everyone.